Not yet come. Your PPT is open.
Yeah,
Yeah,
PPT is
now it has
open.
come. Now it has come. Now it has
It
come.
is done. Okay.
You can put in the slide mode.
Yeah. Okay. Now it's coming, right?
Okay. Okay, I will switch off my mic.
Yeah. Okay. Good morning, everybody. Uh, today is the third lecture from my side. I'll be covering the attitude and orbit control system related activities. My presentation outline is as follows: general remarks about AOCS, terminologies used in AOCS. AOCS and ADCS are, I will be using AOCS or ADCS, both mean the same thing. Elements of AOCS, I'll be touching briefly on sensors and actuators, coordinate systems, fundamental transformation, ECI and orbital frames. How do we represent satellite orientations? There are a few methods like directional cosines, Euler angles and Euler transformation, Euler's eigenaxis rotation, quaternion propagation, and their comparison. And I will also be touching upon today spacecraft environmental disturbance talks. Okay, just briefly to touch upon what is the motivation for AOCS. Primarily to point and maintain the desired attitude as required by spacecraft payload, whether it is communication or imaging. There is also a way where you can have a separate pointing system for the payload, and the satellite provides a chorus pointing system, and fine pointing is provided by the payload gimbal system. What are the spacecraft control and stabilization techniques? General ones. They are spin stabilization, gravity gradient, and three-axis control. See, when the satellite era started, in the beginning, the satellites used to be either spin stabilized, and there were a few satellites in the gravity gradient. But these days, most common method of stabilizing a spacecraft is three-axis control. And the actuators used in the three-axis controls are reaction wheel, momentum wheel assemblies, control moment gyros, magnetic torquers, and thrusters. As far as the sensors are concerned, we have GPS receiver, star tracker, Earth or sun sensors, inertial measurement unit, which measures both the rate gyros and the acceleration experienced by the spacecraft due to the thruster firing. Then, of course, control laws, control algorithms. Then, when it comes to spacecraft slew maneuvers, you make use of the Euler angles or quaternion. Okay, so and those quaternion errors or Euler angle errors are fed to the controller. The key question is, what are the pointing requirements for satellite and what are the limiting factors? As I mentioned earlier, onboard fuel determines the life of the satellite, and the equipment failure can be critical to the mission. What is spacecraft motion? Spacecraft experiences two types of motion. One is a orbital dynamics, that is the motion of the center of mass of the body or the satellites along the orbital trajectory. This motion is specified by position and velocity at a given instant of time in the orbit. Most popular coordinate system is XYZ, and of course, alternately there are you can also express the same information in polar rotation, that is radial vector, azimuth angle, and the elevation angle. Okay. Position and velocity determination is called the navigation, and position control in the orbit is relates to the orbital control. The basic equation of motion we have studied is force is equal to mass into acceleration. And the other type of motion the spacecraft experiences is the rotational motion about its own center of mass. So the orientation is determined and it's called attitude determination process. And you can also change the orientation and that is called the attitude control. Equation of motion, the rotational motion is governed by the equation torque is equal to inertia into d omega by dt. This d omega by dt is the angular acceleration. Here mass is replaced by the inertia, force is replaced by the torque, and the linear acceleration is replaced by the angular acceleration. So that's the difference. There are several ways to represent a rotation: direction cosine matrix, Euler angles, quaternions, etc. We will deal with these in the following slides. Okay, as we have mentioned earlier, introduction, as a part of introduction, attitude is the orientation of a spacecraft in three-dimensional space. Attitude and orbit control system provides the capability to control and stabilize the attitude of the spacecraft, besides providing the orbit control during various phases of the mission, starting from injection into the orbit by the launch vehicle till the end of its life. AOCS system or ADCS system is typically a major spacecraft system because it consists of the onboard computer system, actuators, thrusters, sensors. It has to, and it also has an impact on the spacecraft design and configuration also. AOCS components are cumbersome, massive, and power consuming. In the design of AOCS system, the design, analysis, and testing are typically the most challenging of all the subsystems, perhaps with the exception of payload design and testing. You cannot directly control the test the control system of the satellite. Okay, I have mentioned that in my previous presentation also. And what are the approaches we adopt to step by step to ensure that the satellite will meet its objective? It needs a true system orientation to be successful at designing and implementing an AOCS. What are the terminologies? Common terminologies used in AOCS systems are attitude, which is orientation of a defined spacecraft body coordinate system. That is, you define the X, Y, Z axis of the spacecraft and its orientation with respect to defined external reference. It can be a inertial reference, it can be orbital reference, some frame of reference. Its orientation of the body. Body is defined by the body axis X, Y, Z. Attitude determination is a process of computing the spacecraft attitude relative to either an inertial reference or some object of interest, say sun, earth, or stars. It requires several types of sensors and associated data processes. It can be real time, it can be post facto, either way. Attitude control, maintenance of a desired specified attitude with respect to a given reference within a given tolerance. Attitude acquisition, attitude maneuver from an unknown orientation to a desired orientation. For example, at injection into the orbit, spacecraft may be in the tumbling mode. That is, spacecraft is having a random orientation which is continuously changing. The attitude acquisition process will make the spacecraft point towards the required orientation, which could be sun, which could be earth, etc. And attitude error is a low frequency attitude motion of a spacecraft with respect to the desired direction. And this is the intended topic of our discussion on attitude control. Jitter. Jitter refers to a high frequency spacecraft motion. It is caused by scanning instrument. The spacecraft may be carrying some kind of a scanning instruments for experiments, scientific experiments. It may be carrying a scanning mechanism for the VHRR, that high resolution radiometer, which scans the Earth periodically to take the picture. And it could also be due to the dynamic unbalance of a rotating control element. That is, a momentum wheel or a reaction wheel is a control element. It has a flywheel which runs at a high speed. Now, any static or dynamic unbalance of the flywheel will result in a disturbance which is proportional square of the speed of its rotation at the base of the wheel. And because the wheel is connected to spacecraft body, it will be felt by everybody, all the elements on the spacecraft. So most concerning element is if it, whether it is affecting the sensor or sensor output, and if it is affecting the sensor output, then it will be affecting the control system performance. It could be affecting this input, may be causing a constant input, may be causing the vibration of the solar arrays. So that will be also affecting the body. It will be, this may be also detected by the gyros, and that is fed back to the control system. So that also will be causing a problem. But what is happening is it is generally during the ADCS design process, it is generally ignored. Because higher say these wheels are running, the control system bandwidth is very low, typically 0.1 hertz, 0.05 hertz, that kind of thing. And the wheel, if it is running at 6,000 RPM, 6,000 RPM is 6,000 revolutions per minute, means 100 rotations per second, that is 100 hertz. So that 100 hertz input will not be getting into the control system loop, but the environment, the spacecraft environment will be getting affected. So, but how much is the effect? Larger the inertia of the body, larger the mass of the body, larger inertia of the body, the lesser will the effect, because of 1 over j s square or 1 over j omega square. So omega is 100, higher inertia, 1 over j into 100 square, 2 pi 100 square. So that much, okay. If the input is at 3,000 RPM, the effect will be 4 times. Okay. Now these the input disturbances are reduced by overall good design practices in terms of overall spacecraft configuration by incorporating vibration isolator or isolating the payload platform, or by proper specification and process control during the momentum wheel or reaction wheel fabrication. Agility, we have discussed earlier, how fast the spacecraft can be oriented from one attitude to another. This picture shows you the power spectral density caused by this dynamic unbalance of the wheel. One typical, okay. On this side is the speed, the wheel speed. This side is the various components, various harmonics will also come into picture, and this is the power spectral density. This is I have taken from the literature, so this is very typical, some particular way. Now, attitude stabilization. Attitude stabilization is the process of maintaining an existing orientation in the presence of disturbance torque acting on a spacecraft. Now, what is pointing control definition? Okay, there are three things. This is the target where you want to point it. You use the attitude sensor and estimate the sensor gives its position, okay, which may be this thing, and the spacecraft control system, maybe this is a mean value. On top of it is the low frequency variation taking place. So target is a desired pointing direction. True is the actual position direction. This is true is the mean value, and this cone is showing the low frequency variation. Estimate is the true or instantaneous information derived from the sensors. So what is A? A is the pointing error from the true mean position to the target. That is the pointing error. S is stability peak to peak. That is the low frequency motion around the true value. That is called the stability peak to peak motion. And from the actual position to what is estimated by the sensor, that is called the knowledge error. And because this is what you're feeding to the estimated value of the sensor, you're feeding to control the satellite. So this will be the control error, which is going to the control loop. C is what is going to the control loop. Objectives, I think we have discussed, we will skip. Typical pointing accuracies, for example, for the communication satellites, are pitch and roll less than 0.05 degrees, yaw is less than 0.2 degree. Alternately, it may consist of maneuvering the satellite from one inertial attitude to another and maintain the same over long duration of time for astronomical observation of very faint stars with very high pointing stability. The Hubble telescope is is required to look at faint stars in the far distant galaxies. The signal is very, very low, so it is to look at those stars for a long duration of time. And the field of view of the sensor is very, very narrow. The optics, the camera, the Hubble telescope. So the requirement is the spacecraft attitude should stay within 7 milliarc second over a duration of 24 hours. Some of the things, it is also a requirement over a week, over a month. These are the kind of a thing, stability is required. In certain cases, we need a constant or varying bias for any scanning motion according to the needs of the mission. These are this, what I said, jitter. Jitter is a high frequency component. Say accuracy is a knowledge, attitude knowledge. Okay, from the actual position to what accuracy you are able to determine. So typically 0.1 degree is 3 sigma. That includes attitude determination, attitude sensing, everything. Range is you should be able to, the attitude sensor range will be defined with respect to your nadir or with respect to your pointing axis around a conical region. What should be the range and the accuracy of that one? The drift is the high frequency. The drift is within that low band. What kind of at what rate the spacecraft attitude is drifting within the around the mean pointing axis. Jitter and transit response, like in any typical control system, you say you want to go from one angle, one position or one target position to another, how quickly it should settle, and that's what it defines. These are the elements of ADCS. The central element is the onboard computer, which receives the information from telecommand system to carry out whatever desired functions. And it receives the power from the power system and receives the data from various sensors, sun sensor, earth sensor, star sensor, gyros. processes the information of these sensors according to control law or control algorithms and to give the talking signal to either to the wheels or thrusters or controlling the current in the magnetic torques. It also has an interface with the telemetry, sends the data to telemetry system for the health monitoring parameters, and also has an interface with the payload. I deal with attitude sensors, sun sensors. Sun sensors typically consist of solar cells, and the output of the solar cell is in terms of the current, which is proportional to the solar intensity, area of solar cell, and the angle of incidence with respect to the normal to the solar cells. So this is basically what it is. Now here you look at it. This is the typical analog sun sensor. Here it has a two solar cells in this particular shape, and this is a slit through which is the sunlight falls. Supposing sunlight is no, this is a slit. Well, if the sunlight is falling normal, zero error, then this cell and this cell will be eliminated equally. Equal area will be eliminated. And you take the difference, the output is proportional to the difference of the two solar cell outputs divided by the sum. So what happens is, if you see why you are doing the dividing by sum is basically normalizing. Okay, so and suppose error, so sun will be coming at angle, entering the slit at an angle. So this solar cell will be illuminated more area, and this will be less. You take the difference of these two minus these two. If you can work out the geometry, you will see the output will come out proportional to the error linearly. Okay. Now this is another digital sun sensor. Here, hello. Here also, basically, I'll show you. I have a model of this. If you can see that one. Okay, this is a quartz block. There's a gray pattern. Okay, and the number of the solar cells are mounted below this gray pattern. On this side is the slit. Through this slit, the sunlight will fall and have a particular gray pattern eliminated. And that from that one, you can derive the attitude information, what is the sun angle. Earth sensors. Earth sensors are basically sense the work in the infrared zone of the spectrum. It measures, it detects the contrast between the deep core space and Earth's atmosphere. Earth, as seen from space, looks like a hot body. And as you must have studied in physics, any hot body would radiate over a large spectrum. For Earth sensor, 14 to 16 micron band is selected because in this band, the variation due to the time of day, due to seasonal, are minimum in the Earth's radiation output. Okay, the sensor uses a thermistor bolometer on which the infrared output will fall, resistance varies, and then you can measure. You will be able to process the data of the detectors and find out the attitude errors. Now, in low Earth orbiting satellite, you need because Earth is very large in size, angular size, from 600 kilometers, typically more than 100 degrees. So what you have is you have a scanning motor. So this motor will be scanning the Earth, and when it looks at the deep space, the signal will be low. when doing the scanning motion, it looks at the Earth, the signal will be sensed by the detector, and there are two motors, one on the north side scanning, one on the opposite side, and the difference of the the chord width measured by, if there's any attitude error, say roll error, the chord width measured by one scan will be bigger than the other scan, and the difference will be a measure of the roll error. Similarly, you measure the shift. There is a center reference for the scan mechanism. When it enters the, say from, it is entering, say it is coming from this side. When it enters, with respect to the center of the scanning mechanism, if there is a pitch error, this this distance and this distance will be different, and the difference of the two will give the pitch error. This is explained. This is another type of earth sensor used in communication satellite, which uses a oscillatory system with a oscillation of only 25 degree. Okay, because Earth, as seen from geostationary orbit, is about 14.7 degrees. So you can have an oscillatory type of a system, and it goes out of the, looks at the space, comes back, and looks at the Earth, and again goes back and comes like this thing. So there also the same thing. There are two detectors there. Okay, one north, one south. If there is a roll error, this detector will, this width will be smaller than this width, so difference will be a measure of roll error. And if there's a pitch error, entry of to the Earth to the center point will be different when it enters the Earth and when it exits the Earth and looks at the core space. So okay, and basically a very rough way you can say is, if you can from the chord width, you can also find out the orbital height information. Very chord. Okay. This is, magnetometers measures the three components of the magnetic field as depending on the attitude of the body, spacecraft body. Okay, and you know at a given point in the orbit what is the expected field that is available from the model stored on board. Bx, By, Bz, this is a measurement, and this gives the reference field for zero error. Using this information, you can find out the attitude of the spacecraft. Okay, because with this kind of method, the attitude determination will be very rough, about a degree or so in accuracy. Rate gyros measures angular rate of the spacecraft. Okay, and mechanical gyros make use of the typical law of precession where torque is equal to omega class h. That is, there is a spinning wheel. If you have a rate about one axis, okay, the torque is produced by the other axis, and that torque is sensed by. So what you do is you put the you have a coil, you have a motor, you control the current in the motor to bring it to the null condition, and the measure of that current will be a measure of the rate input. Okay, now there's a one problem with this gyros. The DC bias errors in the electronics will reflect as an output. Okay, now this is a rate gyro. We integrate the rate and we get a angle. Okay, we get omega is equal to d theta by dt. Theta is equal to omega into time plus some constant. Okay, so if there is a bias, electrical bias, which is if the body rate is actually zero, but it is showing some, due to electrical bias, is showing some value. So you will integrate, and the spacecraft will show a increasing attitude information. So what you have to do is you have to calibrate this in orbit. So we'll discuss that later. The other is a optical gyroscope, ring laser. The next one is and fiber optic gyros. The other is a MEMS gyroscope used in this small satellite, nano satellite. They are okay. Basically, there is a oscillatory mass, and it makes use of the because of the body rate, the Coriolis forces are generated, and there's a capacitance that these two masses will experience different forces, and sense their motion using some capacitive method, and to try to find out what the determine the rate from there. Okay, the star tracker is the most accurate type of attitude sensor. It works like a digital camera. It takes a snapshot, and depending on the field of view of the camera, a number of stars will appear in the camera star sensor field of view. Now, there is a catalog of the star sensors stored in the onboard processor of the star sensor. The picture taken is compared with the stored camera, because you know approximately at what time where the camera is looking. So you fetch the data of a certain region of the star catalog from the database, and you compare the star pattern taken by the camera, and then you identify the star. And the catalog also shows you what are the actual direction vectors of those stars. You are now, when you are taking an image, it is a single plane. So, which detector elements are, the detector consists of a CCD array. The CCD number X and Y, Z component to measure, and along with the optics, you find out the direction vector as measured by the star sensor, and compare with the catalog value and find out the attitude in the least square sense, because you have more than 3 stars, and you have so that you, using all the star data, you can find out in the least square sense the best attitude. And these kind of star sensors give the accuracy in arc seconds. This is again a comparison of what I've already told. I'll skip that one. What are the control actuators or devices? These are called momentum storage or exchange devices, consists of momentum wheel, reaction wheel. Magnetic torquers. There are 2 types of magnetic torquers. One is a air-cooled magnetic torquer, other is a iron-cooled. I'll deal with the. In the area of chemical propulsion system, you have thrusters with monopropellant fuel. You have thermal hydrogen thruster. You have bipropellant thrusters. Then you have electric propulsion. Okay. The major sub-assemblies of the momentum reaction wheel consist of a flywheel running at a high speed of say 6,000 RPM, or 8,000 RPM, and this flywheel supported by the bearing, and there's an electrical brushless DC motor which makes it run, and the communication electronics, everything is housed within it. The most critical element is the lubrication system, which governs the life of the momentum wheel. Okay, so the lubrication system supplies constant lubrication to the ball bearing, so that to minimize the friction losses. These are the typical performance parameters. The momentum wheel has a 68 Newton meter second momentum storage capacity at 6,000 RPM. Reaction wheels are smaller in size. They are, we have one set of wheel in slow 5 Newton meter second at 2,800 RPM. We have another one that's 28 Newton meter second at 6,000 RPM. The torque generated are about 0.09 Newton meter. Okay, these are friction torques. steady state power consumption, when the wheel is running at a constant speed, to compensate for this lost torque, you need a power. So typically power is for wheel, but basically higher the RPM, the steady state power will be proportional to 2 pi, omega into the friction torque. Omega is the speed of the running speed, and the T is the friction torque. So this is basically that one. And maximum torque power comes during torquing. When you want to do a control action, you want more torque, and at peak torque and at the peak speed, it consumes almost 100 watts of power, momentum wheel, and reaction wheel consumes 35 watts. Mass of the typical is 8 kg, 4.5 kg, 5.5 kg. These are the actuators used in INSAT, IRS kind of spacecraft. But when you use nano satellite, there are no wheels, micro wheels are there. There the torque will be in millinewton. And the momentum storage, this number is of 68 or 5 will be 0.5, 0.35, 0.25, those kind of numbers are there, which are used in the nanosat. Okay. Instead of 0.09, it will be millinewton. Okay. One order less than this one. Okay. Similarly, the mass also will be very small, 1 kg, 1.5 kg, those kind of things will be there. Magnetic torquer, air-cooled torquer consists of a, basically, you can have a wire loop over the frame of the, over the edge of the spacecraft body. Okay, and pass a current, it will generate a dipole moment, which is proportional to M, which is proportional to number of turns of the coil, current in the coil, and A is the area of enclosed by the coil. When you use a iron core magnetic torquer, the permeability of the core comes into picture. Okay, so the magnetic dipole moment will be like this thing. So the magnetic torque produced by coil depends upon the local magnetic field, of course. Okay, iron core magnetic torque generally provides advantage in terms of power consumption at the cost of weight. That is one thing. Iron core is preferred because of power consumption, but the weight of the core also comes into picture. So that's why it becomes bulky. Then there are attitude control thrusters. Okay, they are located at different faces of the spacecraft for different functions. So you need this thruster to give you talk about they are located such that they should be able to provide a talk about each of the axes. That means you need 6 thrusters minimum to give you positive and negative pitch torque, positive and negative roll torque, positive and negative yaw torque. Okay. So, and in the communication satellite, these thrusters, there are 4 thrusters are located here, 4 are located here, and 4 are located on the south face. Basically 6, 12 is there because of redundancy. An alternate method is, here we are having 8 thrusters. But that here what we have done is we have provided the canting. Now, because of the canting, it produces 2 axis torques. So this 4 thruster in a canted mode can give you the torque in all the 3 axes. Of course, it's not very efficient because at some times it can result in a wastage of propellant also. The propellant minimization will be with this optimal configuration 6 thrusters for 6 direction of torques. Here 4 thrusters, because you have to compensate when you want to talk about one axis, then you have to fire which particular thruster. When you have to talk about 2 axis requirement, what thrusters. So this is not a very optimum thing. But for practical purposes, this is what spacecraft, Chandrayaan spacecraft, the recovery experiment spacecraft. This is a very simplified block diagram of ADCS. Okay, basically you have spacecraft experiences motion in response to the disturbance torques, and the control torques. This motion is sensed by the sensors. Sensors send the feedback, and this is compared with the attitude control command, attitude reference command. This is the target command. The target, and this is the measures the actual. So take the difference, and the control law in response to this difference will generate a certain control demand, which will be asked from the actuator. Actuator will produce. Now actuator control torque is there, disturbance torque is there, and the spacecraft will move in response to both these things. Now let's come to the coordinate systems. How to express the spacecraft orientation in the in the inertial frame, how do we represent in a arbitrary orientation of the spacecraft? There are several coordinate systems used in aerospace application. Each has a property which makes it appropriate to a limited number of applications. Now, I will deal with the various coordinate systems. First, let me come to which is the most important coordinate system. Most important fundamental coordinate system to which all the motions must be referred is the inertial reference frame. Inertial reference frame, in its most general sense, it is a coordinate system fixed with respect to stars. For practical purposes, it is sufficient to select a coordinate system which is not accelerating enough to disturb the problem solution beyond desired accuracy. See, all this, there is nothing stationary. The stars are also moving. And if you take a coordinate system with respect to major respect to some stars position, okay, it is moving. So, then your, the measurement and your computation becomes difficult. So, it should not be moving at a very, very fast rate. Okay, so that is what is a requirement for the preferred coordinate system. Which are the inertial frame of reference or coordinate system? Heliocentric elliptic reference frame and geocentric equatorial, that is Earth-centered equatorial frame, which is called ECI frame. Various other coordinate systems are Earth-centered, Earth-fixed reference frame. Means, okay, I will come to that one. That's called ECF. Then there is a one called northeast up frame, northeast down frame. I'm going to explain each of these. Heliocentric coordinate system. Here, this coordinate system refers to the coordinate system lying in the plane of the Sun-Earth motion plane. The Sun is at the center, Earth is going around the Sun, and that plane is called ecliptic, ECLIPT, ecliptic. And the Earth is equator is tilted by 23.45 degrees with respect to this plane. So this is one, for interplanetary mission, you can use this, particular coordinate system. Here, x-axis, say the intersection of the equatorial plane of the Earth with the ecliptic plane, that is called the line of Aries. So that is defined as x-axis. Z-axis is normal to this ecliptic plane. Y-axis is completely right-hand rule of, okay. So this is called the heliocentric coordinate system. The next one is geocentric equatorial system. Okay, it is called ECI, Earth-centered equatorial inertial coordinate system. Here again, x-axis is passing through the line of Aries, which was in the heliocentric system also. X-axis is common. Y-axis z-axis, here it's perpendicular to the equatorial plane, that is along the north-south axis of this Earth. Y-axis completes the third direction. Okay, so this is called ECI frame, geocentric equatorial coordinate system, or Earth-centered Earth. Okay, and there's other one called Earth-centered Earth fixed. Earth-centered Earth fixed. One is Earth-centered inertial, other is Earth-centered Earth fixed. What is Earth-centered Earth fixed? Here, x-axis passes through the Greenwich meridian, lies in the orbital plane, but passes through the Greenwich meridian. See, all our the aircraft or any other, there are many things which are described with respect to ECI. All our coordinate system, longitude, latitude, is referred with respect to ECEF system. Okay, so here this is a equatorial orbit, and this is the orbit in which the satellite is rotating. Okay, we told earlier also the line of ascending nodes. The ascending node angle is measured where the orbital plane of the satellite intersects the equatorial plane of the thing. That angle measured from ECI is called capital omega. And in the plane of the orbit motion, omega measures the line of perigee. Okay, and from the line of perigee, the satellite position is measured by angle called mu, which is called the true anomaly. Okay, so orbit plane is inclined by angle I. This is omega. So we'll come to the next one and see how we express the satellite position at a particular time in the ECI frame. Okay. Now, one thing is there. I said equatorial, say Earth-centered coordinate system, is it really inertial? No. The answer is no. Because what happens is Earth wobbles slightly, and its axis of rotation, that is, the equatorial plane, is rotating around the perpendicular of the ecliptic plane. It rotates by 360 degree over a period of 26,000 years. So what it means is the line of Aries position is changing. Though this position change is very small, 360 degree in 26,000 years is very, very small. But we have to take that into consideration. Okay, so because of this motion, that line of Aries changing, neither a heliocentric ecliptic plane is fixed, nor the geostationary equatorial orbit is fixed. So what we do normally, since they rotate at very slow speed, what we do is we refer all the motions currently to Julian 2000 year. That means in the year 2000, at midnight, what was the position of that crossing, that is taken as a reference. And everything is computed with respect to that particular point of time. So we say, J2000. Okay, what coordinate system you are using? We say J2000 currently. When INSAT 1 was launched in 1980, at that time we used to take reference of 1950. It was J1950. So these are from time to time, maybe after some time they may change it to another year when sufficient time is progresses. So in corresponding to Julian 2000 midnight of 1st January 2000, what is the position and what are the position of the various stars, it is computed and stored in the star catalog and things like that one. So that is the time we compute our motion and our orientation with respect to that point of time. Now, let me come to,
Okay, Malik Saab, can we have some 5-10 minutes break?
okay,
12
very,
o'clock we can start. Students we can give.
okay, fine, okay,
Okay.
fine,
So
okay.
Karthik, we can start at
Let's
12.
say 11:52, we can start at 12,
12?
because we
12.
lost 10 minutes
Yeah,
in the beginning also.
yeah,
Okay.
yeah. 12 o'clock we'll start. Karthik, can we start now?
Yes, sir. We can start.
Okay.
Yeah, Malik.
Yeah.
Okay.
So we'll start with fundamental transformation. Say you need transformation when you are dealing with various coordinate systems. Okay, normally there will be some information available in one coordinate system, and you are using another coordinate system, so you have to carry out the transformation from one to the other. Okay, so what is the procedure for that one? For example, satellite position and velocity components are expressed many times in more than one coordinate system. I'll give you an example. The magnetic field of the satellite model is available in a particular coordinate system called NED. Now, and you are carrying out everything in the computation in the ECI frame. So you have to transfer that information from the spacecraft orientation from that information to the NED thing and find out the attitude in that frame and then bring back those kind of things are there. Okay. Although, say, for example, a coordinate transformation changes only the basis of a vector. It doesn't change the length or direction after coordination transformation for the parameter, the vector. Vector remains the same. It has the same length and direction after coordination transformation also, but its component will be different in different coordinate system. Now, for example, let us take two coordinate systems, x, y, z, and x1, y1, z1. Okay. Now, we suppose if I give it rotation about this axis by angle theta, so the new coordinates will be y will be, shift to y1 and z will shift to z1. Now, I can write x1, y1, z1 as follows. X remains same because I've done the rotation about x-axis 1, 0, 0. This component y1 has if I resolve y1 along x, y and z, cosine theta and sine theta, and z1 minus sine theta and cosine theta. So I can write down in the vector form in a simple way this coordination transformation. Any vector if I write in this one, okay, if I know the component of any vector in XYZ frame, I can find out those components of that same vector in x1, y1, z1 by substituting in this fashion. I write on the component, I know the components of the vector in this frame, so I can find out in this frame using this method. I'll now give you an example, coordinate transformation between ECI and orbital frame. Okay. So earlier we said ECI frame, the orbital plane intersects the ECI frame or the equatorial frame at an angle capital omega. If I give a rotation first, this is my xi, yi, zi is my basic frame. Now, if I give a rotation about by angle capital omega about zi axis, so I get another one frame by this one. That frame is shifted to this value. The new axis is here. Now, because orbit is treated by angle I, what I have to do is I have to give a rotation about this axis so that this plane which was lying in the in this equatorial plane will shift in the orbital plane. So next rotation is about this axis by I. Now the new plane lies in the orbital plane. Now I give a rotation by omega. I will find out where is the perigee axis. If I give another rotation about now, I get one more frame with whose axis is along the orbit perigee. Now I want to find out the satellite position. From perigee, I rotate the satellite position by angle nu. So omega and nu, since they are in the same plane, I have combined, and the satellite position will is the satellite the position frame is related to inertial frame by this transformation. Okay, you can think about this one. You can okay, and you can carry out you can carry out the same transformation the way I explained, and you will, I'm sure you will come to this. Now transformation from ECI to ECF frame, the same diagram. Okay, I said ECF frame, everything is same. It the except the one axis passes through the Greenwich time. That angle between Greenwich time and the line of Eris are the x-axis, x ECI changes with time. Okay. With respect to the initial frame, it changes. So you have to find out that angle and carry out a rotation about the north-south axis. You will by that angle alpha g. So you can get the angles, the transformation between the ECEF frame and ECI frame. Okay, a simple transformation, simple rotation by alpha g. Now I said northeast. Okay, here, see Earth's potential. Say Earth has a body. Everything is defined in Earth with respect to the Greenwich time. Okay, Greenwich meridian. Our longitude, latitude, everything is measured with respect to that point. Okay. Now, if you look at the gravity potential of the Earth, okay, it is everything is measured with in terms of radius, elevation angle, and azimuth angle in the ECI frame. And our satellite motion we are computing in the ECI frame. So we have to transfer the information, the ECF frame to ECI frame. That's where we will use this transformation. This is just one example. There may be many examples. Okay. Northeast down. Here, northeast down or northeast up, two frames are there. Basically, on the surface of Earth, okay, there is one axis which is going, northeast down, which is from that point, the axis points toward the center of Earth. Other is lying and pointing towards the north direction of the Earth. Third forms a right-hand system. That's a northeast down. Northeast up is same, except this axis pointing down, that axis points up. So that is the only difference. Now, like I told you, the Earth's magnetic field model is, referred to either NED or NEU. I don't remember. Okay, one of the two. Now, our satellite is moving, and it's the Earth is rotating, and the satellite is moving continuously. So that field direction, everything, when the satellite is at a particular latitude and longitude, okay, you draw from that in that condition, you draw a NED or NEU, whichever is applicable at that point of time, assuming a sphere, a fictitious sphere at that orbital height. Okay. Now, the model gives that three components. Now, from this orientation, you have to rotate and bring it to ECF. From ECF, you bring it to ECI. So there is a series of transformation coming into picture. Okay. So here, lambda and psi are measured are the longitude that point corresponding to ECF frame. Okay, so if you know the field direction in along this direction in the as per the model, you can find out from the in the ECF frame. From ECF frame, this is vice versa. If this is known, I can find here, and if this is known, I can find this one. So this is how the transformation takes place. A simple transformation, rotation by two angles, one at a time. Okay. So you can convert that magnetic field information to ECF, ECF to ECI, and and in ECI, if you know the spacecraft attitude, so you can use appropriately. So this is how you carry out the transformations. Now let me come to ECI and orbit reference frame. See, we are generally defining our spacecraft axis as roll, yaw, pitch. Okay. Now, how? Okay, I said reference frame inertial. Inertial reference frame is fixed X, Y, Z. It is fixed frame. Okay, and the orbital reference frame is moving, rotating with respect to orbit, because the way it is defined is x-axis is always along the velocity vector, z-axis is always along the earth center, and y-axis is right-hand sense completion. Now the satellite comes here. So here z-axis is moved. So that means there is a rotation about y-axis at the rate of orbital rotation rate. So the orbital reference is basically rotating with respect to the initial reference frame in this manner. For a communication satellite, I'm saying, for a communication satellite. For a other satellite, also you can do a similar transformation by taking the previous orbital parameters. Just for simple explanation, I have explained like this thing. Okay. A definition. You define, how do you define roll, pitch, yaw for aircraft? Same way. The aircraft is flying, the axis pointed towards the earth below is called the y-axis. The direction of motion axis is called the roll axis, and third axis is the pitch axis. Similarly for ship, similarly for the car on the road. Okay, we define our roll, yaw, pitch in this manner. Okay, how do we represent orientation mathematically in inertial frame? Okay, see, the roll, yaw, pitches are defined with respect to a orbital frame. That is the body. This is the roll, yaw, pitch is okay. Now, if the body's orientation, if it is slightly oriented, so you want the spacecraft to look at the earth center. So you want the yaw axis to look towards this thing. You so define the yaw axis of the spacecraft also. Similarly, define the roll axis of the spacecraft to point in this direction. Similarly, you define in this direction. Now, how do we define the object? Okay, in inertial frame. Orientation of an object can be represented as a rotation of an object from its original unrotated orientation with respect to some frame of reference. There are several ways. One is directional cosines, Euler angles, quaternions. And in all these things, we end up using matrices because it is simple to represent the information in the matrix form. Okay, attitude representation by directional cosine. Supposing you know the bodies x, y, z, the direction cosine of the body, each of the direction, say x-axis of the body, its direction cosines with respect to the three axes of the inertial frame, you can write as in the column form. Okay, so for x-axis of the body, this is body. If you know xb with respect to in this, what are the directional cosines of xb along three axes, you can write down in the column form. Similarly, yb you can write in another column. Similarly, ZB you can write in another column. So you can say XB, YB, ZB is equal to, okay, XI, YI, this matrix into XI, YI, ZI. Okay, so basically this is how it is. Now supposing you want to represent some vector, some length of a vector, what you do is you say Rx, Ry, Rz, and it will give you that information. If any vector is there in this frame, body frame, you can express that vector length in this frame using this matrix. Euler angles is a concept used in rotational kinematics to describe orientation with respect to reference frame. For defining the orientation of a body with respect to reference frame, a series of pure rotations are used, which result in an orthogonal transformation. These associated rotations are called Euler angles, and they uniquely determine orientation of the body. See, normally we use a rotation sequence. First rotation about x-axis, second rotation about y-axis, third rotation about y-axis. It is not necessary this is the only way. You can represent this orientation in many ways. Okay, you can represent first rotation about x-axis, z-axis, y-axis. First, other method is x-axis, y-axis, again x-axis, x-axis, z-axis, y-axis. The number of combinations you can take. Okay, so final result is Euler angles are non-unique and exact sequence is critical. The sequence which you are using becomes very, very critical. Okay, you cannot, you should know in which sequence you have used the rotation to arriving at to be able to properly interpret the information. That is the biggest problem with the Euler angles. A simple example, start by assuming both reference x, y, z and body x, y, z frame coincide. Here, this is a x, y, z is a reference frame. Body is coincide with this one along this thing to start with. Now I give a rotation to the body by angle psi. And the rotation rate about this axis is psi dot. Okay, remember this one. So first rotation, the formula which I explained earlier, so the x1 comes here, y1 comes here. So I write x1, y1, z1 by cosine psi. Now, second rotation I give by angle theta about y1, the displaced axis, and the rate is phi dot. So I write the relation between x1, y1, z1 to x2, y2, z2. Now I give a third rotation about the y2 axis, about the x-axis, and I come to the orientation of the body, where the body should be. So I can now write, substitute x2 here, x1 here. So I can write body xyz body in this manner, beta, gamma, delta. Okay, these three rotations have to happen in this manner. These three matrix will be written in this manner. So that will represent the body. Okay, now this psi dot is called the Euler rate. Phi dot is called, theta dot is called the Euler rate. Phi dot is called the Euler rate. Now, to start with, Euler rate is what is z-axis. Euler rate is what is z-axis. So z1 is also psi dot. I substitute 0, 0, psi dot. So okay. Now when I give the second rotation theta, theta is about the y1 axis. So theta will come here, and x1 was the psi dot. So theta dot and psi dot will come here, and this is 0. So you expand this one. Then what will happen is the last is phi dot. Phi dot will come here, and whatever theta, psi dot, phi dot you have got from substituted will come here. So that is what will give you the Euler rate. This is what omega x, omega y, omega z. It will be written like this thing. You have simplified by, but the basic methodology which I told you was that way. Now, so X, Y, Z is in this form. You can multiply and you will get this one. And you want to do the reverse. That is, you want to find out X, Y, Z from, and you know X, Y, Z, the body. You want to find the inertial frame. So you simply take the transverse matrix. Okay, alpha transpose you will take. Alpha is what? Multiplication, beta, gamma, delta. So which means the sequence alpha will be delta transpose, gamma transpose, beta transpose, and XYZ. So this is how it is. Here, which I explained to you, the Euler rates and body rates. Okay. Now here you see, if I take the inverse of this one, here I cannot take the alpha transpose. In this case, I cannot take because rates were coming about different axes. So this is a difference between the earlier transformation, the vector transformation, position transformation, to this one. Here I have to take phi dot, theta dot, psi dot to find out. I have to take the inverse of this matrix, which is like this thing. So this is a difference you have to remember. So Euler transformation poses a lot of difficulties. Okay. There is another unique way of expressing the rotation. Okay. That is called Euler's eigenaxis rotation. Unique. Say this is our reference axis. To start with, our body is also coinciding with this axis. Now I want to rotate about an axis which is common to both the body and to the inertial frame. That axis is stationary in both the body, is fixed in both the body and inertial frame. Okay, so that is called the Euler axis, eigenaxis. Now I can rotate about this axis. So the body will come like this thing. If I rotate by theta about this axis, this z-axis, the body which was z-axis of the body will make an angle like this thing. If I make a complete rotation, okay. If I make by say angle phi, then this z-axis will come here. Okay, x-axis would have moved by in a plane perpendicular to this cone, and y-axis would be lying in that one. Okay, here you see. Okay. Now what is happening is this Euler axis is fixed in the body. So okay, it has a certain direction cosine matrix, direction cosine values, and phi is the angle by which you are making a rotation. So normally we said we need three angles to describe a motion. Here we need direction cosine of the eigenaxis and the amount of rotation. That means comes to four parameters. One is extra. But here you see direction cosine matrix E1 square plus E2 square plus E3 square is equal to unity. So if I know two parameters E1, E2 or E2, E3 or E3, E1, the third one is automatically fixed by this one. So I need to know only two of these parameters and the angle of rotation. So that satisfies my three parameter requirement. I had planned to, because of shortage of time, I can explain in details more mathematics form, but because of shortage of time, I have skipped that explanation. Okay, now this, E1, E2, E3 in this picture is represented as Kx, Ky, Kz. And the angle phi in this picture is represented as angle theta by how much rotation. And these three are called the vectors, and this is called the scalar quantity. So E1 sine phi by 2, E2 sine phi by 2, E3 sine phi by 2, Q4 is cosine phi by 2. So this represents a scalar quantity, this represents a vector quantity. Okay, using this information, the spacecraft attitude orientation can be uniquely defined. It doesn't come into any singularity, nothing. Okay, if you see in the previous picture, here, if theta is 90 degree, cosine theta becomes 0, this becomes infinite. So it is not properly defined. You get into a singularity condition. That condition will not come in this kind of a approach. Okay, now this quaternion can be propagated using this value. So you can define your attitude in the quaternion form, okay, and you have a body, the spacecraft body is undergoing complex rotation, simultaneous rotation about all the three axes, okay. So by measuring the rate of the body axis using gyros, I can propagate the simple attitude with time. I can write this equation in this form, where this capital omega represents this skew symmetric matrix. Okay, I can define Q vector quantity, and this has a 3 by 1 column, 3 by 1 column, and I can represent this Q matrix, this vector in this form, scalar in this form. Okay, this is very easy of representing. Similarly, I can take out instead of omega 1 outside inside, I can take omega 1 outside and do this one. Okay, these are the manipulation of this simple quantity. Like I said, I can propagate the Qs, the attitude of the spacecraft, using only the body rates. Now, in the earlier equation, you saw sine and cosine were coming. Here in this propagation, nothing is coming. Here, Q1 is equal to a simple summation. So you are avoiding trigonometric function, and the computation becomes very, very simplified. So this, in a step-down inertial reference system of aerospace vehicle, body rates are measured by the rate gyros, which are fixed to the body of the spacecraft or the aircraft. See, aircraft also is the same thing. Spacecraft also is the same thing. So the step-down gyros are fixed to the spacecraft body, and you use this thing to propagate the attitude. Now, question is, Q dot is like in a simple ordinary differential equation, dx by dt is equal to a, x is equal to a t plus some constant initial condition. The constant depends upon the initial condition. Here, if I start Q with 0, 0, 1, Q dot will give me the change from that point. But absolute, what is that point when I started integrating? That at absolute value I have to know. That for that purpose I need a sensor. A star sensor will tell me what is the Q value, what is the attitude of the spacecraft in terms of Q at the starting point. So I take that attitude from the star sensor, then propagate with time. I get the attitude of the spacecraft continuously. Instead of star sensor, I can use magnetometers or a combination of Earth and Sun sensors, any sensors. Okay, any absolute sensors should be able to give me. Okay. Now, of course, the gyros, when I'm using rates, earlier I mentioned they have suffered from electrical biases that cause drift. So the gyros, that drift has to be also computed and compensated. Now, since you have, you make use of a Kalman filter, which continuously take this gyro input and the star sensor output, and computes the gyro drift and provides the value to be corrected in the gyro output. That goes on in a continuous basis. Okay. I wish the time was there, you would have appreciated how these Qs are derived. Okay. Maybe if you are interested, the next lecture I can cover that one. Okay. That I know it is difficult to grasp, but the shortage of time, I skipped the detailed mathematical derivation. Now, what are the pros and cons of different techniques? Either angles. No, it is simple thing. It is you need psi phi theta, then the unique orientation defined. The rotation is in a unique way and orientation is defined in a unique way. Earlier I mentioned, because theta becoming 90 degree, you get into gimbal lock. So this is a singularity which comes into the use when we use Euler angles. So this is a negative point. And you need to define the sequence of rotation has to be defined in a particular manner to get the uniqueness of the result. Eigen-axis quaternion approach. Quaternions have no such inherent geometric singularity as do the Euler angles. Quaternions are well suited for onboard real-time computation because only simple mathematical operations like addition, subtraction, multiplication are involved. And no trigonometric operations exist in the quaternion differential equation. Provides attitude control capability through short path. Say, you are, that angle, you are defining the angle of rotation phi, which I said. Now, supposing one way is I can, suppose I want to rotate by 90 degree, or I can rotate by minus 270 degree. This method gives me to have the rotation in the shortest path, that is 90 degree, instead of minus 270 degree. Okay, so or 30 degree instead of 330 degrees. So it gives me a flexibility of the shortest path approach. Okay, let me come to the new topic, spacecraft environmental disturbance talks. Types of disturbance talks experienced by the spacecraft. There are two types of talks. One is the external talks experienced by the satellite. One is the internal disturbance talks. There are two types. The environmental disturbance talks, external disturbance talks experienced by the satellite fall in the following categories. These are gravity gradient talks, aerodynamic talks, magnetic talks, solar radiation pressure talk, thermal radiation pressure talk. Others like mass expulsion, that is leakage of thruster, leakage of tanks, are the jettisoned objects. Assessment of the expected disturbance torques is an essential part of rigorous spacecraft attitude control design process. The relative magnitude of one with respect to other depends upon the satellite orbit, satellite shape, and optical properties. These torques depends upon various factors. Most important is the orbit and the shape of the satellite, and then also the optical properties we will discuss subsequently. The first one is the gravity gradient disturbance torque. Any non-symmetrical object of finite dimension in orbit is subject to a gravitational torque because of the variation in the Earth's gravitational force over the entire object volume. See, this is an arbitrary object. The one mass element dm here experiences certain force. The mass dm, another mass dm experiences higher force. So when you sum it up together, all the forces integrate over the body, the expression turns out to be in this manner. Okay. Now, when you simplify, make small angular approximation, because phi theta, you are normally looking towards the Earth center, small deviation in terms of roll and pitch, etc., is coming. Then in that case, what happens is the disturbance torque can be approximated in this manner. Here you say, if Izz is greater than Iy or Ixx, the gravity gradient torque will act as a destabilizing. Okay, this expression will come to subsequently. So what I'm saying is, depending on the initial properties, this torque can be stabilizing or this torque can be destabilizing. The gravity gradient torque vanishes for a spherically symmetrical satellite. That is when the object is symmetrical. That is all the inertia about all three axes are common. About any axis in the spacecraft, inertia is same. In that case, gravity gradient torque does not exist, so no disturbance. Okay. Since it is a function of omega naught is the orbital velocity, this angular velocity of the orbit is a function of the orbital height. It is higher for the low Earth orbit. So it is a dominant source of disturbance torque in the low Earth orbit. It can be dominant source of disturbance or corrective, both. In low Earth orbit, it is more effective than the other torques. Next is the aerodynamic torque. The interaction of the upper atmosphere with spacecraft surface produces a torque about the spacecraft center of mass. For a spacecraft with orbit height less than 400 kilometers, the aerodynamic forces and resultant torque is the most dominant aerometric disturbance torque effect, both in terms of orbit decay and attitude disturbance torques. The force due to impact of the atmospheric molecules on the surface of our spacecraft can be modeled as an elastic impact without any reflection. Okay, the incident particles energy is generally completely absorbed. The torque due to aerodynamic on the surface of element area of AR is given by the cross product of the center of pressure minus center of mass and the aerodynamic forces. So the torque will come if the center of pressure is different from the center of mass. If the two coincide, then only the orbital, it will affect only the orbit. If the two are not coincident, then it will result in a rotational torque. And the force is half rho. Rho is the atmospheric density. CD is the coefficient of drag. AR is the projected area in the direction of the velocity. Okay, and V square is the velocity. And this represents V dot N. That is what should I say? The vector direction for the disturbance torque. That is velocity, and if the some surface is at an angle to the velocity, then that cosine component will come, because AR is a projected area along the velocity direction. Okay, so if it is a net area, not a projected area, so this will make the cosine effect, cosine angle will come. Okay, I think I have already said, because parts of spacecraft may have different drag coefficients, like solar panels, for example, act like a big sail. Drag forces on different parts of the spacecraft can also differ. The drag coefficient is different, the surface properties are different. Okay, so drag coefficient, so you have to compute for each element and sum it up. Therefore, one can take the contribution of individual surfaces along with the distance between center of pressure, where the drag acts, and the center of mass, and sum it up. Next is the magnetic disturbance torque. It is results from the interaction of spacecraft residual magnetic field M. This residual magnetic field comes due to a combination of various factors, such as permanent and induced magnetism and the spacecraft generated current loops. Okay, see, the current is, there are various circuits, various things are there, current loops are there. So some kind of a, the magnetic field will be produced by those loops. So those will interact with the Earth's magnetic field, residual field of this spacecraft will interact with the Earth's magnetic field and produce a disturbance torque, which is nothing but M cross B. M is the residual dipole moment of the spacecraft magnetic field. B is the Earth's magnetic field. Earth's magnetic field is a complex, asymmetric, not non-aligned with the spin axis, and varies with both geographical movement of the dipole and changes in solar particle flux. But for practical purposes, we can take the Earth's magnetic field as a dipole, and the dipole is tilted from the Earth's north axis by 11.3 degree and lies in the plane along the 69 degree west. Okay. So recently there was a lot of news was there that the Earth's magnetic dipole is varying very fast. In the recent a couple of months back, it was in the news. The tilt, the direction is changing very fast. Not this 69 degree and 73 degrees, moving very fast. Solar radiation pressure. Solar radiation incident on spacecraft surface produce a force at the center of pressure, which results in a torque about the center of mass. These forces are due to the impingement of photons on the spacecraft surfaces. See, the solar input is coming, the solar radiation input is coming in the form of photons of high energy particles. Okay, and when the photons impinge on the spacecraft surfaces, they produce a force. Solar radiation varies as the inverse square of distance from sun. That is 1 upon r square. From sun to from sun to earth, the orbital height, the distance so large, this orbital height will not really matter, whether it is 600 kilometers or 36,000 kilometers. So for all practical purposes, we can assume the solar radiation force is constant for the Earth orbiting satellite. Okay. The major determining factor determining the solar radiation pressure talks on the spacecraft are again geometry of the surface, its optical properties such as absorptivity, reflectivity, and diffusivity. Orientation of the sun vector with respect to spacecraft surface and its appendages. What is the solar radiation pressure? It is a very small number. 4.63 into 10 to power minus 6 Newton per meter square. See, this number is very small, but its cumulative effect over time results in a matter of concern. Okay, that results in a momentum buildup. We will discuss that one. Okay, now let us assume in general a fraction, say unity is the number, unity is the number input is coming from sun. A fraction rho s of the impinging photons are reflected like a mirror. Fraction rho d is reflected diffusively and fraction rho is absorbed by the surface. The diffuse reflections may be considered as having stopped at the surface and subsequently re-radiated uniformly into the hemisphere. See, rho s plus rho d plus rho a is equal to 1. Okay. Now, this is what I said was like this thing. This is the spacecraft surface. Its normal is along this thing. The solar input is coming in this direction at an angle theta. Now, a part of rho a fraction is absorbed. Okay, when it's absorbed, it pushes in this direction. Okay, now I said a part of it is getting reflected like a mirror. So in angle of incidence is theta, reflected is theta. Part of it is getting stopped and getting redistributed in all the directions, like in a diffuse light, diffuse bulb. It is happening like that one. So this is how rho A, rho S, rho D. Okay. Now when we sum together, mathematically we can work out the number comes out to be F solar comes out to be solar pressure, projected area, n dot S is the cosine factor, and this is along the sun vector, and this component is along the normal to the surface. Okay, so and this is cosine theta will be coming to picture. So you can work out all this, how much is along the north vector and how much is along the south vector, and mathematically it can be simplified. And solar radiation, the torque is acting. If the torque is acting at the center of mass, if the force is acting at the center of mass, no torque is produced. So center of pressure minus center of mass into F solar. Okay, this is the torque produced. Then there is another type of thermal radiation pressure torque. See, absorbed radiation from sun causes a material temperature to increase relative to the surroundings. Sunlight is falling on this solar array. You take, for example, I'll give you a simple example. Okay, the space which is looking at sun will be hot. The back side is looking at the space. Okay, the hotter side will re-radiate the as a thermal radiation, as a following the Stevens-Boltzmann law. Okay, and backside also depending on its temperature. So there is a temperature difference. So there will be a imbalance force. Now that imbalance force will be acting at the center of the solar array, geometric center, and geometric center of the solar array is away from the geometric center of this entire spacecraft. So it will produce a torque. So basically, I said solar array, for example, has the sun-facing solar cell side higher temperature compared to backside, which faces deep cold. The radiation emitted by the sun-facing side will result in a torque acting on the spacecraft. Reaction forces caused by thermal radiation is arrived at assuming a diffuse emission of radiation from each of the exterior surfaces, and thermal radiation forces on elemental area can be written as F thermal 2 by 3 Q by C A. Q is what? Total thermal radiation follows the Stevens-Boltzmann law, which is proportional to sigma emissivity and T2 power 4. Okay, in watts per meter square. This is the Stevens-Boltzmann constant. Emissivity of the surface depends upon the emissivity of the surface, velocity of light, temperature of the surface. So this is. Now this shows pictorially, it's not for a particular thing, it shows pictorially how the different disturbance torques act. See, drag torque is, atmospheric torque is acting at a lower altitude compared to, as altitude increases, atmospheric density comes down, this practically disappears beyond certain height. Similarly, gravity gradient torque also is dominant, is a function of the orbital height, but also it is a function of the initial properties. So it also eventually becomes smaller and smaller and smaller. Same thing with the magnetic field. As the orbital height increases, the Earth's magnetic field will be reducing as a function of 1 over r cube. So this magnetic torque also comes down. Now you see the solar radiation pressure, like I mentioned, solar radiation pressure is irrespective of the orbital height, because solar radiation pressure is, is a constant number. Okay, for near Earth satellites. So solar radiation pressure is remains constant. There are other factors like mass expulsion. Due to thruster, any misalignment is there. When you fire thruster, it will produce a disturbance torque over the other axis. Outgassing and propellant leakage. If there is a leakage of the propellant, it produces a disturbance torque on the satellite. If the outgassing is there, say, there are material when, goes to space, vacuum, at low temperature starts, boiling, things boiling. And depending on the material, the outgassing also can cause, and we have seen this outgassing effect very often in the initial phase of the spacecraft, when the spacecraft goes to the geostationary orbit. First 2 weeks of the geostationary orbit, when we enter geostationary orbit, the first 2 weeks, we have seen many times very large disturbance torques because of outgassing. But then subsequently it settles down. What are the other type of torques are the internal torques. Internal torques are defined as torques exerted on the main body of the spacecraft by internal moving parts such as, see, momentum and reaction wheels. Also, when they rotate,
Malik
I am
Sahab, this,
two slides over the last
okay.
but one. So momentum and reaction wheel produce when they rotate, the reaction is felt, opposite reaction is felt. If they rotate clockwise, the reaction on the body is felt anti-clockwise. They can be used for the purpose of control, but they produce a disturbance. Okay, they will discuss that one. Similarly, control moment gyros, scanning instruments. Okay, see, the first two can be used for the control purposes, but they produce torque on the, okay, and how that torque is made use of is we'll discuss. Scanning instruments, any scanning motion of the instruments inside the spacecraft will produce a disturbance torque, which will be affecting the spacecraft attitude, and which has to be corrected with momentum and reaction wheels. Liquids inside partially filled tanks, okay, fuselage. Additionally, torque resulting from vibration of lightly damped flexible appendages. Then there are cryo coolers for cooling the detectors, pumps, etc. Okay. In addition, the disturbance torques arising from the crew motion in a manned spacecraft also come in this category. But the important thing is to remember the internal torques do not result in the change of total momentum of the spacecraft. Only the external disturbance torques result in change in total angular momentum of the spacecraft. This is what we will see in the subsequent slide. Concluding remarks. Okay. Like what I was repeating, only the external disturbance torque results in momentum buildup. Internal torques and consequent momentum exchange from the scanning instrument, for example, result in momentum redistribution with the control elements, such that in the absence of external disturbance torque, the total angular momentum of the system remains constant. What I'm saying is, when you have an internal disturbance torque, like a scanning instrument, it is having, when you scan, it has a certain momentum. Okay, that momentum will get redistributed to the control element, momentum wheel or reaction wheel, such that total sum remains same. Okay, thank you. That's all for today.
The next lecture will continue on the control part, no?
Yeah. I think most likely the next lecture will be Monday. I will need 2 lectures.
Yeah.
Probably I'll try to
Yeah,
finish
probably
off
we'll.
okay, because the material was too much. In fact, I
Okay.
wanted to, that quaternion I wanted to show in the details, but
Okay.
the shortage of time, because that is very important for people to appreciate the motion,
Yes.
how the spacecraft, everything is in terms of quaternion these days, all the spacecraft's control and all. So in the next class, I will be covering the passive control techniques, the active control techniques, and the control laws, and the factors which the governing factors for the control system design. But I think I will need 4 hours, 2 classes.
Okay.
Monday and Thursday, or only Monday?
Yeah,
Monday.
whatever way you want.
Okay. I'll come back to you. Okay. Meanwhile, any question is there, you can note down and
Okay.
send it to me. I will.
Yeah, that's fine. Now, students are aware that 2 o'clock we'll have a session on STK.
Yes, sir.
Okay. Good. Okay, so thank you.
Okay.
Thank you, sir.
Thank you. Welcome.